Hello, dear friends. Today we will be going over Projectile Motion Lab 2 for Physics 2111 by Lawrence Val. Introduction. The purpose of this lab was to study projectile motion by tracking a thrown object and comparing the experimental data to computational models based on Newton's second law. As you can see here, we have a projectile motion and an initial position. Next, wait a second. Wait 1 second. Is it recording? I think so. Experiment and data collection. In this experiment, we recorded the motion of a thrown object, in this case a polymer eraser with a mass of 0.0252 kilograms. The motion was a two-dimensional projectile. The camera was kept stationary to avoid distortion, and a calibration stick was used to set the scale in the tracker. The coordinate system was placed with the origin directly below the release point. Using tracker, we extracted position data over time, which allowed us to analyze both the horizontal and vertical motion of the object. Physics principles and models. The motion separated was into the x and y axis. The horizontal constant velocity, the vertical acceleration was just the force of gravity, and I'm sure this picture explains it all. Now onto our computational model. I used the sample code from the introduction or the instructions for the lab, and I calculated the initial velocity from tracker and just took my position. I used Newton's second law. The model updates velocity and position over time using a time-stepping method. First, I modeled motion under gravity alone, assuming no air resistance. Then I added a drag force proportional to the square of velocity acting opposite of the motion. This allowed me to generate predicted trajectories to compare with experimental data. Data and model comparison. This is essentially the graphs that I got from tracker. I just compared my experimental tracker data with the two computational models. The gravity-only model predicts a perfect parabolic trajectory, while the drag model better matches the real-life version. It accounts for air resistance. The horizontal motion remains linear, confirming constant velocity, while the vertical motion is curved due to acceleration from gravity. And these other graphs are pretty helpful as well. The black points experimental data, the blue line is gravity-only model, and so on. Now, what does all of this mean exactly? The gravity-only model does not predict terminal velocity because this is a not opposing force. The drag model does, since air resistance increases with speed and reduces acceleration. In our experiment, the object didn't travel long enough to reach terminal velocity. If the object were thrown straight up, it would take longer to hit the ground because it travels upward before falling back down. This shows that including drag makes the model more realistic. These are our what ifs and our interpretation. Common sources of air and projectile motion experiments in general, and including ours as well. There's air resistance. This affects drag accuracy. Tracking points can introduce positional errors. You can't always be perfect with tracker, especially because you're just left and shift clicking. The initial conditions, such as the speed and angle, can vary slightly, and human error, such as recording and all that as well, it's not really the best thing to base an experiment off of, but this is just a rudimentary one. In conclusion, projectile motion follows a parabolic trajectory. Gravity is primary force. Drag effects slow down motion over time. The ideal motion models provide baseline predictions, but reality requires accounting for air resistance and other things. Good agreement was found between experiment and drag model overall, I'd say. The end.